It gives you this table that you're going to be using in question 6. And this table is something that I have seen on a diploma exam before. And you need to be able to interpret it. I've got a little key that I put in here at the top left that tells you what beta decay is in terms of the table and tells you what alpha decay is. On the bottom of the table, it's scaled as atomic number, and the vertical axis is scaled as atomic mass number. So the bottom number is the number of protons or the place on the periodic table. The number on the vertical axis is the sum of the nucleons. If we were to go back, and I'm just going to go back and do one of these ones here. If I were to ask you to predict the product of alpha decay when thorium-230 undergoes alpha decay, it's really pretty simple. You need an 88 in the denominator, and you need a 226 in the numerator. So the top numbers, I guess they're not really denominators and numerators, but I think you catch my drift. The top number is nucleons, which are conserved, and the bottom number is charge, which is conserved. Again, everybody, the bottom number is also number of protons, but it doesn't always have to be numbers of protons. And then you look at the periodic table, you find number 88, and I believe it's radium. So if you look at what happens during alpha decay, and this should make sense to you, the atomic number, the bottom number, always goes down by 2, but the top number, the number of nucleons, always goes down by 4, because it's 4,2 for alpha. And that's why on this chart, an alpha decay is represented as going from one place diagonally down and to the left, and it goes to the left 2, but it goes down 4. Do you catch my drift here? That's why that red arrow in the key is alpha decay. If you were to look now at an example of beta decay, oh, there's one there, lead-212, 82 Pb, that's 212, and it undergoes beta decay. Of course, you need to know that there is an antineutrino produced as well. And then the top number will be 212 and the bottom will be 83. Ethan, does that make sense? Okay, we can look up 83. I'm thinking bismuth, or it is bismuth. And if you look at what happens during beta decay, everybody, the top number stays the same, and all that happens is the atomic number goes up by 1. And that happens because a neutron changes into a proton. But during beta decay, what happens is the atomic number goes up by 1. Which is why if we had something like lead, well, I don't have lead-212 on here, but I have lead-214. If it undergoes beta decay, it's still 214, but it becomes bismuth. It goes up by 1. So that's understanding the chart. What question 6 is asking you to do is the Herculean task of starting with uranium-238 and writing the alpha decay of uranium-238, and then the beta decay of that, the beta decay, the alpha decay, the alpha decay, the alpha decay, etc. And I put this question in here not to give you a whole bunch of work, but to introduce you to the idea that there's something called a decay chain. I told you that something undergoes radioactive decay because it becomes more stable. But it doesn't become as stable as it can be until sometimes it goes through a series of them. So if you wanted to do this, you would start off with uranium-238. You don't have to look up the atomic number of uranium because it's given right on this chart. It's 92. And in order for its atomic number to go down by 2 and its atomic mass number to decrease by 4, it's got to emit an alpha particle, and you will have 234 on the top and 90 on the bottom, which I think is thorium? No. Yeah, thorium. Now, we could check something here if I've read my periodic table right and I understand alpha decay right. This point right here should be thorium-234. And when I look down from this point, Ethan, matches thorium, and when I look to the left, it matches the 234. What I would then do is take the thorium 234, so we're at this green dot, the thorium 234, it undergoes beta decay to get 234, but it's going to be 91, because the 91 plus the -1 has to give you the 90. And then we could look up 91, and 91 is protactinium. And then we would continue. So there's this decay chain, and what I have done is I have written 2 of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have written 2 of the 14 links in this decay chain. And I'm going to stop there. But that's what the task in front of you is for question 6. And I don't have the answers up here, but if you look at the answers on the next page, I think, yeah, a couple of pages in, you will see it is actually on the next page. Number 6, it lists them all, right? I mean, this is certainly not something that would be asked on an exam, although I could give you this chart and ask you certain things about it. Like if, and I wouldn't give you this. That's the learning part. If we start off with uranium-238 and it turns into radium-226, what are the series of decays that occur? And it would be alpha, beta, beta, alpha, alpha. Are you okay with that? Okay. Does anybody have any other questions you would like me to go over from this? Okay, and don't forget, if you are trying to find the energy released, you have to compare the initial and final masses, which you can get from a table or from the question. If it were on an exam, I would give it to you in the question. You'd see in the question the mass of this and the mass of that. Okay, we left off yesterday with this example, so I would like you to turn back to example 2A, which we finished. And I need to explain something about beta decay in terms of your textbook and that table that's on page 881, which is also on the back of your periodic table. So what I'm explaining to you is not a physics thing directly, it's just a procedural thing about solving problems from your textbook. I would like you to get out that table. So get your periodic table and look at the back side of that handout. We've got that table which comes from page 881. Even though someplace in your textbook it calls that table a table of nuclear masses, it turns out it's a table of atomic masses. In other words, when you look at that table at the mass of whatever, uranium-238, and you see that number of atomic mass units, that is not just the mass of the nucleus, it's the mass of an atom. What's the difference? The difference is the atom has electrons. So those masses, if you look up, for example, the mass of thorium-234, and I can show it to you. Oh, it's right up there. The mass of thorium-234 is 234.043601 atomic mass units. That's the mass of the thorium-234 nucleus and all of the electrons surrounding it. In other words, that's the mass of the 90 protons and the 144 neutrons together in a nucleus and 90 electrons surrounding that nucleus. All right? Because atoms are neutral, they have the same number of protons as they have electrons. Because of that, when we take a look at what's happened here, we had 90 electrons. We still have these 90 electrons swarming around this new nucleus. But that means that this protactinium is not an atom. It's 1 electron shy of being an atom. Because if it were an atom, it would have the same number of electrons. So this little box that I've hidden from you, you can choose to put it now in your notes. It's a positive sign. And I've never seen this. Well, I'm not saying it's rare. It's just that in my experience, I've never seen this except for this textbook. And the first time I was reading this textbook and I looked at that and I noticed there was a plus sign there, I thought that was a typing mistake or a printing error, but it's there for a reason. It's telling you that that protactinium is 1 electron shy of being an atom. Are you with me on that? Okay. That is not important for writing the beta decay of thorium-234. If you wanted to write the beta decay of thorium-234, you could simply put this without the plus sign there. The plus sign is there so that I can explain to you how to get the correct answer in the next question. Okay. So the next question says, what is the energy released by this beta decay that we've already looked at? All right, so we've already done this. And now we've added that plus sign there. So now we're going to find out the energy released. Well, you know that to find the energy released, you have to compare the mass before and the mass after. And by the way, if the two masses were equal, then there would be no energy released and nothing would change. But something does change. So when we look at our table, and I've got it in the top right corner there, the mass that we start off with is 234.043601 atomic mass units. Now, when you look at these three things, we have to put all of their masses together numerically. We have to add the numbers together. I say it that way because when you combine the masses into a new particle, there's a mass defect, and that's not what I'm talking about. So we need to take the mass of a neutrino, an antineutrino, which I will tell you right now that the mass of an antineutrino is so exceedingly small, it's not worth our consideration in these calculations. Later on, after the new year, when we get back, I will show you what the actual mass of an antineutrino is, and we might need to use it then, but we're going to ignore it. Now, when I write down the mass of the protactinium, I have a problem because this number up here, the number in your table, is not the mass of this thing in the reaction, because that thing in the reaction is missing an electron. Still with me? But luckily, there's a beta particle that's produced, not out of nowhere, it's produced out of the neutron changing to a proton, but there's a beta particle here that has a mass equal to the mass of an electron, because a beta particle is an electron. So these two things together are this mass. That extra beta particle mass-wise takes up the slack of that protactinium missing an electron. And that's why when we calculate the mass here, we just use the mass of the protactinium. And the first time I checked one of these problems in the textbook, I added the mass of an electron and I was getting the wrong answer and I couldn't figure out why. And the reason why is the numbers from the table are not nuclear masses, they're atomic masses. Which is, again, normally you see a nuclear mass table, not an atomic mass table. So when you are doing beta decay calculations from the textbook, you need to remember that you have to, it's not that you're ignoring the mass of that beta particle. You're saying the mass of that beta particle is included in the number from the table. And from here on in, it's clear sailing. All we have to do is subtract these two masses. And you'll want to follow along on your calculator and make sure you're getting the same numbers as I am. I'm sure you will. I mean, I know these numbers are right, but you want to make sure that you're getting the same numbers. So when you subtract the two, you get negative 0.000294 atomic mass units. When I multiply that by the number of kilograms per atomic mass unit, which is 1.66 times 10 to the negative 27 kilograms, I get that mass in kilograms. And I just need some affirmation from you that you're getting the same thing. And you are. Okay, good. So what do we do with that? Well, if you're asked to find the energy released, then we have to basically say to ourselves that the reason the mass is lost is because the mass that is missing from the universe now has been converted to the energy that is released. And the conversion from mass to energy or energy to mass always follows Einstein's E equals mc squared relationship. Or maybe more specifically for this course, delta E equals delta mc squared. So we multiply that by the speed of light squared and we get an answer that's negative 4.38 times 10 to the negative 14 joules. That negative, particularly for you chemistry students next semester, a negative change in energy means exothermic. But again, in chemistry you use H instead of E. Use H for heat, I suppose, is the reasoning. We were also asked, where does the energy released go? Well, it goes into the kinetic energy of the emitted particle, primarily. You do need to understand something else, though. The nucleus itself is going to recoil backwards, like a gun will when you fire a bullet from it. So there is an amount of energy as well that goes into the nuclei's kinetic energy. Plus the antineutrino has energy. There's some kind of energy associated with it. Does anybody have any questions with 4B? I think it was 4B. Doesn't matter. With part B. Okay, so that's alpha decay, that's beta decay. Now let's discuss gamma decay. What happens during gamma decay? Well, since the particle emitted, and I'm using the word particle loosely, since the particle emitted during gamma decay is a photon, and I could have just as easily said photon created, because it wasn't like there's a photon just sitting there inside of the nucleus somehow waiting to leave. It doesn't exist until the decay happens. Since a photon is a little bundle of energy, that energy has to come from somewhere, and it comes from the nucleus losing mass. But it doesn't lose mass because a particle left. It loses mass because it loses energy. If I am moving from one place to another, and my very last trip, I go through my old apartment or wherever I was living, and I got a box, and I just pick up some odds and ends. My tape gun that I was using for packing. Oh, there's some dishes and glasses and my coffee maker. And I throw it all in this box, and I put it in the back seat of my car, and I drive to my new place. But I go over some bumpy roads. When I get there, I will have noticed that everything in that box will have settled down. Right? Will have shifted. And the reason it does so, I mean, you can say it does so because gravity finds spaces, but it does so because that new arrangement of all of those things is more stable. I mean, if I just delicately put stuff in there in a precarious manner and I shake the box, nature will settle it down to make it more stable. So what does this have to do with gamma decay? Well, in a nucleus, you have a whole bunch of protons and neutrons that are separated by certain distances. They're not touching each other. They're separated from each other. And sometimes the way they're arranged is not very efficient. It's not very stable. So they will rearrange and move closer together. And they become more stable. And if something becomes more stable, it emits energy. So we actually talk about energy levels within a nucleus. If you look at my hands, and anybody watching the video will miss out on this, but it might be that when the nucleons are in this particular orientation, we would say the nucleus is at a high energy state. And there might be another arrangement that's a little simpler or a little more stable, and that would be a lower energy state. It's very similar to an electron in an atom being at a high energy state and a lower energy state, except it's the whole nucleus, which means that they could continue to get more and more and more stable until they become so stable that they're as stable as they're ever going to get, and that's referred to as the ground state of the nucleus. It's not about electrons, it's about the arrangement of the nucleons. So here's an energy level diagram. It's a nuclear energy level diagram. It's not an electron energy level diagram for carbon-12. And there's a question here that I want you to consider. This is, by the way, this diagram is purely symbolic. It's not saying this is what a nucleus looks like, right? It's just a diagram showing numbers. I want everybody to think about this question. And you know what? I could even cross this out and put carbon. If we had an energy level diagram, an electron energy level for carbon, how does this nuclear energy level diagram for carbon, how is it significantly different than the electron one? There's something about it. Liam? Yeah, this is millions of electron volts. Right? When you take a look at the vertical axis here, it's millions of electron volts. And all of the energy level diagrams we've looked at, they don't even get into 100 electron volts. It's either single digits or maybe getting into the double digits. But you would never peak past 100 electron volts. And yet this is millions of electron volts. So think about this for a second. I hope things are going to start to come together. When an electron in an atom, which is not this diagram, when an electron loses energy, it loses a couple of electron volts or so, or maybe 10, or maybe half an electron volt. And what happens when that atom loses energy is photons are created. But when the electron goes down energy levels, the amount of energy gives us infrared photons, or visible light photons, or ultraviolet light photons. Because it's not a lot of energy, but if we lose millions of electron volts, guess how much energy, rather guess what type of photon that big amount of energy corresponds to? Gamma ray photons. So that's the bottom line. Let's take a look at a quick example with gamma decay. Cobalt-60 undergoes gamma decay with a photon energy of that. What is the decay equation? And explain how the nucleus changes during the decay. So we're going to have to look up the atomic number of cobalt. It's cobalt-60, so that 60 kind of helps me locate cobalt because I'm looking, and we haven't talked about this, I guess we should. Can you look at carbon on your periodic table? You see the number 12.01? We don't use that number in this class. That 12.01 in chemistry is 12.01 grams per mole, right? But it is an atomic mass number. Why, when we have carbon in physics, just when we're studying carbon, we have carbon-12, we have carbon-13, we have carbon-14. Why does it say 12.01 up there? Evan? It's an average of all of the isotopes, which tells us that according to the most recent measurements, there's a heck of a lot more carbon-12 in our universe that we observe or know about than there is 13 or 14 or 11 or whatever other isotopes there are. There's talk of changing some of these numbers, and I think some of them might have already changed. There's talk of changing the carbon to 12.02, I think. So, you know, your sons or daughters or granddaughters or your offspring are going to maybe have a periodic table with slightly different numbers. So we don't use those numbers directly, but this will help me locate cobalt because I'm looking for something around 60. Right? It's not going to be exactly 60 because this will be an average. There it is right there, 58.93. So it's number 27. I'm not even sure why they give you the numbers on our periodic table. They give you them, don't they? Like you see 12.01 by carbon? Yeah, we would never use that. So cobalt is 27. Okay, so here we go. It emits a gamma ray photon, which has no nucleons and no charge and a symbol of the gamma letter from the Greek alphabet. So what do we have left? Well, if the nucleons are conserved, we still have 60 up top, and we still have 27 on the bottom because charge is conserved, and I don't know that we need to look up number 27 again. You get the idea that it's cobalt, and we have a problem here because the cobalt on the left is not the same as the cobalt on the right. It's different. The nucleons in the cobalt on the right are in a more stable arrangement. The cobalt on the left is more excited, unstable, than the cobalt on the right, and we indicate that by putting an asterisk by it. It's just a notation that tells us and physicists that that particular thing will undergo gamma decay because it's not perfectly stable. And I have seen, you might say, well, maybe this is still not perfectly stable. I have seen 2 asterisks on the first one and 1 on the second, but not in this course. How does the nucleus change? You give me one change in terms of the description or the structure or something about the nucleus. What's one thing that's different about the nucleus? Evan? It has less energy. So the nucleus lost. Can you tell me how much energy the nucleus lost? Yeah. It lost 1.1732 million electron volts. But, and this is the really tricky, slippery thing about nuclear physics. That energy wasn't energy before the nucleus lost it. Like there wasn't that energy. The nucleus didn't really have that energy and then gave it up. What did the nucleus give up to produce that energy? Farhad? Mass. So this is the idea of mass, energy, energy, mass. They're the same thing. This is a really good way to put it, but if we trace it back to the actual properties of the nucleus before, what this means is the nucleus lost so many kilograms, right? And I like that you're grabbing your calculator because you can figure out how much that mass is by using E equals mc squared. This is going to be, since delta E equals delta m c squared, this will be the energy change over the speed of light squared. But of course we have to use joules. There are other ways to do it with electron volts, but I would rather not do them that way. So we are going to take 1.1732. Did I write that number down from the original question correctly? Okay. Times 1,000,000, which is 10 to the 6. This is the number of electron volts I need to multiply by the number of joules per electron volt. So this is the energy. If I divide by the speed of light squared, 3 times 10 to the 8 squared, the mass of the nucleus decreased by, I mean, it's a pretty tiny number, but it's measurable. 2.09 times 10 to the negative 30 kilograms. We could also say that the nucleons rearrange themselves. That would be another change that happened. Classic exam question would be, during the gamma decay of cobalt, 60, a photon of energy 1.1732 million eV is produced. What is the mass loss of the nucleus? Or I give you the mass of the nucleus before the decay. I tell you the energy of the photon that's produced, and I ask you to find the mass afterwards. So you would have to go, okay, I got to subtract that mass to find the lower mass. Farhan, you had a question.
No, I'm just confused. I thought you said like the first, like the initial atom loses like energy and it loses mass. But
The atom, the nucleus, loses mass.
it gains energy.
Well, it doesn't gain energy. The mass that is lost is converted to energy, which is released in the environment. Which is why I said it's slippery. These are both, technically speaking, a nuclear physicist would say these are both true. And we will even get to the point where I will tell you that the mass of a particle can be given in electron volts. Its equivalent energy. So the first and second statements are both true, but from a standpoint of physics 30, I think this is the best way to go. You can think of the energy that was lost as being energy that was in the system disguised as mass, is maybe the way to go. You okay with that now? Okay, any other questions from this example dealing with gamma decay? Yeah. No. No. You mean in the neighborhood of 10 times the mass of an electron? No. I mean, there might be some deeper meaning there that I'm not aware of, but the mass lost for big nuclei, or not for hydrogen, small ones, the mass lost is typically during decay in the neighborhood of, during gamma decay, 10 to the negative 29, 10 to the negative 30. It's just the way it is. I want to be careful about, if we were talking about alpha decay, the mass loss, you wouldn't include the mass of the alpha particle during alpha decay. You wouldn't consider the mass of the alpha particle during alpha decay as a mass loss in the system. The nucleus loses that mass, but it's still there in the end. I just want to make sure you understand when we say mass loss, we're talking about it's just not there anywhere to be found anymore. And I don't know why I started answering that or saying that. Anyway, I think, Evan, you had a question. Oh, it was about the electron, right? And then I got onto alpha decay. But I've answered your question. Okay. It's just a fluke that it's in around that neighborhood. Any other questions before we go on? Go ahead.
So those two statements are the exact same thing, just with different units?
Yes. They seem contradictory because, you know, if you look at this statement, which is what I would like you to focus on. Evan said the first one, which is true, and it's used to explain why the second one is true. But the second one is true because during a nuclear reaction, you always lose mass, and the reason we lose the mass is converted to energy. Okay. At the same time, I've said mass and energy are the same thing. So if I say energy is lost, I can say mass is lost, or vice versa. It's the difficulty that arises when you look at that conservation of / mass energy. What the hell are we, pardon my language, what are we talking about there when we say mass energy? Are we talking about mass, or are we talking about energy? We're talking about mass if you convert all the energy to mass. We're talking about energy if we convert all of the mass to energy. And you know what I would say? Don't overthink it. Any other questions? Okay. So now we get to positron emission, which is beta positive decay. So there's beta decay, which we finished studying today, and we started yesterday, and there's something called beta positive decay. The first thing to understand is when you see the phrase beta decay, we're talking about negative beta particles being emitted. Positron decay can also be called beta positive decay, and the particle that's emitted is a positron. And a positron has no nucleons. The atomic mass number on the top is 0. And that positive one on the bottom is not protons, it's charge. And I hate to break it to you, but what a positron is a positive electron. Okay? Almost every electron in the universe is an electron. It's negative. But sometimes, for various reasons, nature pops out particles that are exactly the same as an electron. Like if you could look at an electron in one hand and a positron in the other, they don't have colors. This is just an analogy. They would have the same color. They would feel the same. They would have the same sponginess or whatever texture they had. They would have the same kind of surface touch. They'd have the same charge. They'd feel the same in terms of heft, but one would be positive and one would be negative. So what a positron is if you could take an electron and make it positive. Okay. It probably isn't a big surprise to you that when a positron is emitted, a neutrino is emitted as well. Oh, there it is at the bottom. Because when a beta negative particle is emitted, an antineutrino is produced. So if I switch the type of particle that's emitted into a positron, I get the opposite type of neutrino. I get a regular neutrino. We will talk more in the new year about why there's very little of this stuff. This is called antimatter. You guys have heard of antimatter? Maybe from movies or something. There's matter and antimatter. Matter and antimatter are two types of matter that if they come into contact with one another, they annihilate each other. They disappear from the universe and are replaced with energy, which sounds very science fiction-y, but it's true. So if you were walking down the street and you met an anti-you and you shook hands, you'd be gone, along with a huge amount of energy being replaced. So let's write the decay equation for the positron decay of nitrogen-13. So we go to our periodic table, we locate nitrogen, which is number 7, and it's nitrogen-13, so we put a 13 up top. We're told it's positron decay, so we need to know that you get this positron particle, plus you get a neutrino, and you figure out what else you get based on conservation of nucleons and conservation of charge. I guess the top number is still going to be 13, and the bottom number would have to be 6. You know, it's really surprising how easy it is to mess up this number when it's just the one you're dealing with. Because if it's -1, this number goes up, and if it's +1, it goes down. And I've seen really strong students just write the wrong number, write 7 there, because they think it should be 7, or write 8 rather. So the bottom number, 6 plus 1, adds up to a total charge of 7. It's correct. We looked that up. I think that's carbon, isn't it? Okay, so it's carbon. So there is the decay equation for nitrogen-13. Now, I don't believe I put it in your notes in this example. Does it say, describe the net change that occurs? Oh, it does. For some reason, I don't have it here. I'm not sure why that is. So we're going to do the same thing here that we did back here when we were dealing with beta decay. Remember, we counted all the protons and neutrons before and after, and we compared them. So what do we have to begin with? We have 7 protons. We have 13 neutrons. This changes into a, well, there's a lot of ways to write this. I'm going to write this way, which is a little bit odd, isn't it? Because we're used to that E being electron, but I'm just going to put a positive there because it's a positive electron. Plus we get a neutrino, which has no charge. And then we have, what else? We have 6 protons and 7 neutrons. I've made a horrific mistake over here, haven't I? It's not 13. It's 6. I have to take 13 minus 7 to get the number of neutrons. It should be 6. How embarrassing. So we get 6 neutrons and 7 protons turning into a positron, a neutrino, 6 protons and 1 neutron. So of those 7 protons, we still have 6. Like there were 7 protons swimming around somehow in the nucleus, and all of a sudden one's gone. Hey, where'd he go? That means that 6 of those protons did not change. They're still there. So the net change, this is like a net ionic reaction almost, is to say that 1 proton turned into 1 positron plus 1 neutrino plus 1 neutron. I want you to notice, by the way I've written this, which is different than what I did yesterday, the charges on the top balance left and right. I've got a positive 1 charge on the left and I've got a positive 1 on the right. If you compare this, which is positron decay, which you are expected to be able to describe, in other words, multiple choice question, during positron decay, a proton changes to a neutron and a neutron changes to a proton and you have choices. If you compare that to beta decay, and I'm not going to write a beta decay equation, but that's where you have an electron and an antineutrino produced. And you can go back in your notes and see this. This is what the thing looks like. And this is what I was getting at near the end of yesterday's class, which is this is a real puzzler. Because we're concrete thinkers. Humans are concrete thinkers. They want to know what something is like and how things fit together. And, you know, if you ask somebody who doesn't know anything about nuclear physics, you tell them, well, you have this thing, and it turns into these things. The immediate reaction is to assume that those 3 things were fitted together somehow to make that first thing. In other words, that thing fell apart into pieces, which would mean that this neutron is smaller than a proton because it fits in a proton. That's a reasonable explanation. It's wrong, but it's reasonable. And when you look at it here, you say, well, this thing turns into these 3, so these 3 must have been parts of the neutron, which means the proton is smaller than the neutron. But the first line says a neutron is smaller than a proton. It doesn't make sense. It's not pieces, it's changes. And right near the end of the unit, we will explain what's going on, and it turns out that inside of here, and inside of here, and inside of here, and inside of here, there are other particles. Okay. Any questions with that positron decay example or about this discussion of the changes of the nucleons? All right, we have one more thing we're going to cover. And I hate that Alberta Ed does this, but there is nothing in the program of studies, which is what students are required to be taught, what I have to teach you. There is nothing about electron capture, other than to say students should be familiar with other nuclear processes such as electron capture, etc. And for the longest time, the diploma exam said, we're not going to expect students to know the details of electron capture. So they would show you this as part of an exam question. You turn the page, you look at the question, you go, okay. A nuclear process called electron capture occurs when a nucleus absorbs an electron and emits a neutrino. The resulting nucleus then emits a series of gamma ray photons to become more stable. And then below that on the exam, it would give you this question. What's the decay equation for the electron capture of potassium-40? And what they've stopped doing is they've stopped telling you this on the exam. So I guess I'm telling you you're expected to know this. just as well as you know alpha decay, beta decay, positron decay, gamma decay. A big key is the phrase electron capture. Electron capture. That means that what you have is, in this case, potassium 40. Is potassium number 20? 19. And it captures an electron. For some reason, there's an electron at a very low energy level. And I'm personalizing the electron, and it's just an analogy. But that electron looks down, sees the nucleus, says, hey, that looks like a good place to be. And it goes into the nucleus. What that means is that this electron is one of the things you start with. It's added to the potassium nucleus. It's not produced. It's taken away from the environment. So what do we produce? Well, look, we're told, and I'm going to reason this out for myself. We should be told that a neutrino is emitted, correct? Now, this is how I remember that a neutrino is emitted, or how I figure it out. This is totally different what I'm going to write down here. During beta decay, regular run-of-the-mill beta decay, you produce an electron. We can put beta there, but it's an electron. And you produce an antineutrino, right? So I follow this kind of law of symmetry in physics where I say if you change one thing, the other one has to change to be symmetrical. So if that electron is on the other side of the equation, that antineutrino has to switch as well. It either has to go to the other side of the equation or it has to become a neutrino. I don't know if that's helpful, but one way or another, you need to know that if electron capture occurs, you get a neutrino. And what else do you get? Well, you just use your conservation of nucleons to get 40. And I want everybody to figure out the bottom number. (18). Okay, because these two numbers here are on the left. They add up to 18, so the charge is 18 before. That means we need a total charge of 18 after. And we look up 18, which is argon. And to put the cherry on the top of this, we can put an asterisk there because we're told, and we should kind of know that this is almost always the case. When most decays occur, you're never left with something which is 100% stable. It's probably going to undergo a series of gamma ray decays, but you're told that in this question. So what happens? I'm curious. I always like to see or figure out how my students are thinking. How many of you see that what's happening here in general is that a proton changes to a neutron? In general. Because you have 19 protons to begin with and then you only have 18. You're losing a proton, right? That's not how we're going to do this. I just wanted to see your reaction, and apparently not too many of you see that. Why do I know that that lost proton has to be creating a neutron? Evan? It's still 20, right? It's still 20 nucleons. So if you lose one, you have to gain the other. But what you want to do here is figure it out. We've got 19 protons. We've got, is that 21? 40 minus 19? Okay. It's time for a break. 21 neutrons. We also have an electron, and we get a neutrino, which I should have written. Well, that wasn't the neutrino. That's the neutron. We get a neutrino, and we get, what do we have? 18 protons and 22 neutrons. So when you compare the protons and neutrons, we lost a proton and gained a neutron, which means during electron capture, a proton and an electron come together to produce a neutrino, and a neutron. A lot of weird stuff. Any questions about that final example today or about electron capture in general? Go ahead.
I just want to know if this could be compared because potassium is in the first group of the periodic table, and considering like valence electrons and how all of the elements want to be like the noble gases, could that be compared to the stability?
It's a great question. I think the fact that it's potassium is a fluke. I don't know. But you're saying this turns into a noble gas, which is more stable chemically. And I think that's a great observation. I don't know that we can compare chemical stability to nuclear stability. If this reaction occurs, if electron capture does occur with potassium, and I don't know that it does, I just made up this example, it's going to occur to make the nucleus more stable. And if the electron structure becomes more stable, as an added bonus, then it just is an added bonus. I don't think there's a direct connection. No other questions then? All right, so you got a fair amount of time today. The practice for day 2, there are some textbook questions. There are some additional problems. I would encourage you, maybe if you have time today or over the next couple of weeks, to try some of these other textbook questions that are listed here from yesterday. So I don't know if you want to take your textbook home. You have access to the electronic version of the textbook anyway. And don't forget that you're using that errata that I gave you yesterday for answers for textbook questions. All right, so get to work on that. I will come around and I will give you a hand.